Try again. So, according to our favorite acronym, what would you let me be? All right, so LIATE, no logarithmic, and the second letter I for inverse trig function. So U is arcsecant x dx, and dv has to be everything else. I'll take this part while y'all work on arcsecant. Everything else is x dx. Yes, ma'am.
If we had something like this on the test, would you give us the, like, formula for the derivatives?
I would love to say yes, but Miss Hinton told me it was really important to know the inverse trig functions for calculus 3. There are a few other things we have to integrate. When I said, like the second day of class, hey, there's only 2 more integrals to remember, I didn't tell you that there's a lot of other things to remember. We know all of our definite integrals now, but I mean, that's still something that if it's not the day before the test, I have to look it up. The day before the test, I make sure I know it. I write it at the top of my test. The day after the test, I don't remember it again. Honestly. So what is the derivative of arcsecant x? All right, because I remember when I'm integrating u times the square root of u squared minus a squared, that is arcsecant x. Typo. I remember my whiteout picture. My best friend. You don't make mistakes. You can't find a mistake on me. And v is what? This one's a dx right here. All right, is all that good? So that integral, that's arcsecant, which I said I can't spell, is u times v minus the integral of v du. That's going to clean up some. I'll go ahead and bring the 1/2 from the v out in front of the integral. And I'll have x squared over this x just leaves me an x to the first in the numerator. Did you have it cleaned up to that, Miss Cheryl? Oh, that would have made it so much better. Yes. Yes. That denominator, if you think of it as being x squared minus 1 to the negative 1/2, then the derivative of the x squared minus 1 is 2x, and we already have the x, so we just have to have a 2, and we'd have to put another 1/2 out front. And dx. You can finish it from there. All right. Let's talk about through that. Okay. Let's talk about 8.3 is trigonometric integrals, and I just want to quiz you on a few things real quickly. I don't mean pop quiz. And by the way, I am seriously thinking that if y'all hold your homework up to face me each day, I'm giving you a 6. This is all I have time. This is more of a almost like an attendance grade. If you're here and you hold up a piece of paper with writing on it, I'm giving you a 6. It's okay. It's okay. This is beautiful. Are you doing math in ink too?
Huh?
Are you doing math and ink too?
Oh, I had ran out. I didn't have a pencil last night.
Oh, okay.
I started it.
But you usually
I
like
started
pencil?
coloring mine because it was so many lines and it hurt my eyes to look at a giant block of blue.
hurts to look at.
I know. Okay. All right. Here's what I want to quiz you on real quickly. It's easy. Section 8.3, trigonometric integrals. I want you to tell me these 4 definite or indefinite integrals and the first 2 Pythagorean identities. Pretty much they just exist. If you need it in another class, you'll say I saw it before. But we really don't pretty much. Yeah. What's the antiderivative of cosine x? Is it positive or negative? It's positive because when you take the derivative of sine, you just get cosine. What's the antiderivative of sine x? Because when you take the derivative of cosine, it gives you negative sine, and that's not what you want. So you have to have negative cosine in order to get a positive sine. What's the antiderivative of secant squared x dx? Because the derivative of tangent is secant squared. And what's the antiderivative of secant tangent? All right. And remember the first 2 Pythagorean identities? Because we're going to use them a lot today. This is basically what we're using today, those 6 things. Now, what 8.3 is about is powers of trigonometric functions. For example, what if we had secant to the 5th or a sine to the 4th? The key is going to be if we can write it as something that we can see. Oh, here you go, Jordan. Which, on Tuesdays, do you have time to hang around?
Yeah.
Okay, see me. If we can write something in the form just u to a power with du beside it, we can use the power rule to integrate it. So the key is going to be how many, if you give me, well, let's just start with sine cubed. Yes. Sine cubed x dx. At first glance, you should be able to use the power rule on that. You could put sine x in parentheses with the cube outside. Oh, but if it's the power rule and you have sine cubed, when you differentiate it, you not only add 1 to the power and divide by the power, what do you have to have beside it? The derivative of the sine. So somehow we have to write that as something that has, we can use the power rule, but we have to have the derivative of the sine beside it. I could write it as, yeah, we just got to figure out how. I could write it as sine x squared times a leftover sine x dx but that doesn't seem all that helpful because sine is not the derivative of sine. Sine's the derivative of cosine. Mm-hmm. That would at least, like, yes. Like Emma said, that's 1 minus cosine squared x. And we're not quite there yet, but at least I have something now that the expression inside the parentheses has part of the derivative of it outside the parentheses. I may have to distribute that sine x so that I can do this term by term. If I distribute the sine x, I have sine x dx, which I know I can differentiate, minus the integral of, I'm going to write it cosine x with the square outside so that I can see why it's the power rule, and then sine x dx beside it. What's the antiderivative of sine x dx? And I usually don't think of the negative at first. I write down cosine x and then go, wait a minute, if I take the derivative of that, I'm going to have a negative. I don't want to have a negative. So that means give me negative cosine x. And then it's important to look at this as you're not integrating cosine, you're integrating ugly squared. And you have the ugly outside it. So what's the integral of ugly squared d ugly? 1/3 ugly cubed plus c. Now there's only one other thing I need to check. And when I take the derivative of negative cosine, that gives me positive sine. What about when I take the derivative of this cosine cubed? What's that going to give me? When I say this is ugly squared d ugly, I'm not being totally honest because the derivative of that ugly is negative sine dx. I'm going to go ahead and say, that'll make my sign straight. Yeah. And I think I would be a better teacher if I said, if I left that negative there and said du has to be negative sine, you would see why all of a sudden that changed to a positive. All right?
Turn the negative into a positive by like attaching That's so cute.
Whatever works. Whatever works. That's the hardest thing to explain in a way that kids understand it. No, well, yeah, but that's hocus pocus. That's cute, but one,
Cute.
adding a negative, you're adding a subtraction into your checkbook, you're subtracting. But why is minus a negative adding? If you void multiple checks, if you wrote 10 checks for $20 each, then you would subtract 10 20s out of your checkbook. But then if you voided those checks, you'd have to add those 10 20s back in. And for a kid that hasn't had a checkbook yet, that's kind of hard to explain. Okay, number 2. Starting out with easy ones. They're going to get a little bit harder, but if you understand the goal, you don't have to keep looking at that page of notes. You don't have to get that tattooed on your eyelid before the next test.
So those things show like the formula or something?
Yeah, we're not going to look at those for a minute.
Okay.
I want to convince you that you can figure this out. What's your idea? I know if I'm using secant as my u, then I have to have secant tangent as my du. So this is really, and I'm putting in all the steps I can think that will help you, but you're going to start skipping steps pretty quickly, and that's okay. If I write that as secant cubed x times secant x tangent x, I'm going to go ahead and, I don't have as many steps to this one. I'm going to go ahead and write that as secant x in parentheses q. Is that equivalent to the line above it? Is it ready for the power rule? Yes. Add 1 to the exponent divided by the exponent. It's all in training your brain to see what it needs to see. What gets a little bit uglier, and then there's a few weirdos thrown in, but what gets a little bit uglier is just when the argument of the trig function isn't just x, maybe it's secant of parentheses 5x plus 4 or 5x squared plus 4. That could be uglier, but we're learning to see how to separate the trig function into one of these basic 4 guys. And in this section, they only deal with sine, cosine, secant, tangent. There's no cosecants, cotangents. Thankful for little things. All right, number 3. First thing, I'm going to have to split that tangent, but I don't yet see. If tangent's just going to be my u, then what's the du? Give me an idea. All right, let me try that. Tangent squared x times secant x tangent x dx. Yes, that's the thing to realize on this one is I can't leave it in terms of tangent because tangent doesn't have a secant in its derivative. So changing that to 1 plus, tangent squared would be secant squared minus 1. we have it in terms of secant tangent is the derivative of that. But like we did on number 1, I need to distribute that secant tangent so that I can integrate it term by term. If I called that whole thing u, then it wouldn't be the derivative beside it. So, secant squared times secant tangent minus 1 secant tangent. This is u squared with du right beside it. So what's the antiderivative of secant squared? Mm-hmm. And then what's the derivative of secant tangent? Nice. Okay, I have one more before we get to ones in the book. Doesn't it? It looks so simple.
It does.
It just looks like, well, obviously, add 1 to the exponent, divide by the exponent. But you don't have the derivative of u beside it. Okay. So, what's your first suggestion? Tangent squared times tangent squared? Okay. Then what? And then what? That's what we've done before. Okay. So let's call this secant squared x tangent squared x minus dx. Again, dx. Minus tangent squared x. It's possible. Yeah, look at the guys we know. Figure out how to get one of those. Okay. Because what function has as its derivative tangent squared? I said, what function has its derivative secant squared? Yeah. And then what function has as its derivative just 1? Yeah. That's plus x because I have minus and negative. Oops, sorry. All right, what about that first guy? So, you're saying, if it helps me, I could write that as tangent x squared. And then what's the derivative of tangent beside it? Yep. So what's the antiderivative of tangent x squared? Now, the reason I wanted to start with those is I don't want you to have to memorize this, and I certainly don't want you to come in with this tattooed on your whole body for the next test. Yeah, I'll catch you looking down your shirt because you got it all on your belly. That's the only place it would fit. It makes sense that when sine or cosine are odd, and it says and positive, but we're not going to see any power negative exponents in here. So just when the power of sine or cosine is odd, you need to get one of the sines or cosines to be the du, and then write the others as u to a power. And same thing with secant. If you have secant to an even power, then you want a secant squared, and you can write everything else in terms of tangent. And then the derivative of tangent is secant. Let me try that one more time. Write everything else in terms of tangent, and then the derivative of tangent is secant squared. And then when you have an odd power of secant, you can say a secant tangent for the du and write everything else in terms of secant to a power. Now the thing that is a little bit tricky, and if we have time, we'll look at this example. It may not be 519. I may have forgotten to change that page number. But example 5, whatever page it's on in the whatever edition we're in, you're going to get to one in the homework that's secant to an odd power. I can even tell you which one it is tonight. If you write in your book on number 23, you might make yourself a note. See example 5. You have 2 in the homework that are integration by parts. I'm so sorry. 13 and 23 are both integration by parts.
You monster.
I didn't write the book. That's why I don't write a math book. I don't want people cursing me for eternity.
I would never curse you.
23, yeah. Look at example 5 if we don't get to it. Okay, if you are stuck, you can't figure it out, and then you look back at the notes, here's the note about secant to an odd power. And that's when you're going to go, oh yeah, and you look at example 5 for that. But it's absolutely cool if you figure it out without doing example 5. Just remember my words. That will serve you well in life.
It always does.
2 other things that we will run across and need. When we have even powers, see these first 2 guidelines are odd powers of sine and cosine. When we have even powers of sine and cosine, we might need these 2 things. And gosh darn it, I think your brain is full. I'll give those to you on the test.
Thank you.
All right. Let's see how many examples we can get done. Number 10 looks so much worse than before we just did. It's just life. Is that the life lesson or what? You were all cheerful until you wrote it down. I love Cheryl so much. You have to laugh or cry, you might as well laugh. You tell Michaela we're having a Christmas party and she's invited. I know, I miss her. Okay, so any ideas? Yeah, I mean, this was the most obvious thing to rewrite. It's not a huge step, but a baby step. What baby step can we take here? Times what? Okay, now I just said we weren't going to have negative exponents, but let me just say we're not going to have to, let's just keep up with that sign to the negative a half a minute and figure out what we can do with the cosine. What do you think? Could we write everything in terms of sine? Well, we have a Pythagorean identity that would let us write everything in terms of sine. We could get sine to a power, but what would we have to have beside it? Which is, okay, so we need all of those cosines except for one to be sines.
So we should get
Mm-hmm. And again, I'm writing down steps that you're probably going to be able to skip after you just do a few. Okay, then what? As what? What if I did this? This would look like this. She's forgotten full. She is so deep in calculus, she's forgotten the word full. Yeah, because if right now, if we let this be u, this is not du beside it. We're gonna have to, we're gonna have to flow it out. Okay. 1 minus 2 sine squared x plus sine to the 4th x. I think I'm going to have to. This is not difficult. This is tedious. It is definitely tedious. But if we distribute that whole sine to the negative 1/2 t cosine t, then everything will be in terms of power of sine, and the derivative of that will be out to the side of it. So sine negative 1/2 t cosine 2. Yes, how about that? And S stands for sine. Okay, I completely have lost an argument here. I've lost my X's. Let's try that again. Minus. Oh, that sign's the negative. That T's not part of the exponent. When did it jump up in the air? Just, okay, I got a little wonky there. Because I'm thinking X's. And that I'm X's in this problem. Sine 21 T, sine squared T, plus sine to the fourth T. Oh, geez, that's a lot of tape. Tape is my best friend. Jeez Louise. Alright, let's try that. Sine to the negative 1/2 T cosine T dt minus 2 sine square of T 2 sine square of T cosine T dt plus sine to the fourth T sine to the negative 1/2 T cosine T dt. I promise you, you'll be able to. I broke it into 3 integrals when I distributed this. You're right, and it goes right here. And I think that is. I think we can do it now. It's really not. Because now this first integral is just sine to a power with cosine beside it. How do we integrate sine to the negative 1/2? I'm gonna save integrating for one step. I'm gonna write this as sine t to the negative 1/2 with cosine t beside it. And I could write the second integral as negative 2 integral of sine to the what? With cosine t dt beside it. And plus sine to the what? Integral of sine t to the and all 3 of them are just a power rule. And 1 to the exponent divided by the exponent. multiplied that 2 times 2/5. That's about as much cleaning up as we could do. It's tedious. I agree 100% it's tedious, but was it actually difficult?
Just recognizing what happened to go down.
I think simplifying tends to be the hardest part of calculus.
Yeah, I do too. I think we figured that out pretty quickly. I mean, that's only, the 5th one we've done, and we said we could write everything as sine to a power and leave only one cosine beside it. As soon as you realize that, the rest of it's just tedious. All right, I wish we could get 2 more. I bet we can only get 1 more. Trying to think which one. 12 was a little bit ugly, but I want to do something that doesn't have just sign in it. I want to do something with, y'all pick one. 22 to 34. Let me see. Huh? Okay, let's do 28. By popular demand, number 28. 26 is just too ugly because of the pi x over 2. Takes forever just to write it down. 28 tangent to the 5th x times secant to the 4th x dx. What do you think?
I see 2 secant squares.
Yeah, I'm starting. My first thing was clean it up and
Since the derivative of tangent is secant squared, if I wrote everything in terms of tangent, then I could make a secant squared right beside it. That's what I'm thinking. So, this is already in terms of tangent. Maybe. Let's try that. Tangent to the 5th x, and then that is secant squared x times secant squared x, and then you're wanting to write one of the secant squareds as well. And then you'll end up with how many integrals? Because you have a tangent to the 5th with a secant squared x dx beside it. And then you're going to have the integral of tangent to the what? You're happy again. Miss Samantha's going, I can do this. I can do this. Okay, what do you tell me what you don't get? Okay, let's talk first about how I thought to do that. Because that's the hard part. I said, as soon as I saw that I had a secant squared, anytime I have a secant squared, if I can write everything in terms of tangent to a power, then secant squared is going to be the derivative of it. So I thought, how do I write that as everything but that secant squared in terms of tangent? Oh, I can write secant squared as 1 plus tangent squared. And then I'm distributing both this and this to both of these terms. So tangent to the 5th secant squared x times 1 is that. And then tangent to the 7th times secant squared is that. And then it's just the power rule. What's the first, the antiderivative of the first term? With the derivative of the ugly right beside it. And then 1/8 tangent to that 8. Yep. All right. You will encounter a couple that are worse than what we did. No doubt. Most of them aren't, but that one, 13 and 23, specifically number 23, where you have to look at example 5, that's going to be a little bit uglier, but we'll talk about whatever we need to tomorrow morning. Did everybody, let's see, did y'all see this? Okay, okay. Sam's already chosen his university. He doesn't need it. Mal went to Tech. She called it Big College. I'm going to Big College now. UT is Big College for sure. All right. I understand. I have to say that was better than it was last year. I have. It was that writing down the stuff that we wrote down first, the stuff we remembered, that made a difference. We didn't look at the paper first and go, oh my gosh, I'm going to have to memorize all that.